Now, the physiology we've looked at so far is describing the way that the body tries to compensate for a hypoxemia. We're describing compensatory mechanisms. And clinically, if we look for these compensatory mechanisms, if we see them occurring, that alerts us to the fact that this patient is becoming hypoxic. And that's what we need to intervene to prevent. And this physiology is very nicely explained in what is called the oxygen flux equation. Now, the oxygen flux is the movement of the oxygen from the lungs through to the cells of the body. Flux is just the movement. So, oxygen flux equation is oxygen delivery from the lungs to the tissues of the body. And that concept is called oxygen flux, the movement of this oxygen. And it's determined by simply three factors. The first is cardiac output. The next is arterial oxygen saturations. And the next is the hemoglobin concentration. Now, let's think about the cardiac output first of all. Remember when we were looking at the truck? The truck was going back and forward, picking up oxygen and taking back carbon dioxide. Well, if the truck was going back and forward 10 times a minute, as opposed to 5 times a minute, you could carry more red bricks. And it's exactly the same with the circulatory system. Cardiac output describes the volume of blood pumped out by the left ventricle in a 1-minute period. And if that volume is higher, there's more red cells going around the circulation, so there's more red cells circulating to carry the oxygen. There's the same number of red cells, but they're going round quicker. So they're able to carry a greater volume of oxygen, just as if the truck was zipping back and forward quickly, carrying more red bricks in a 1-minute period. And that's why you get an increased cardiac output and we see a tachycardia, because it's an attempted cardiovascular compensation to improve the delivery of oxygen to the hypoxic tissues. The next point is the arterial oxygen saturation. Now, saturation refers to the proportion of the available oxygen carrying capacity of the hemoglobin in the blood, which is actually occupied by hemoglobin. So it's the red cells in the hemoglobin that carry the oxygen. They can carry 100% oxygen, which should be fully saturated, but if they're only carrying 90% oxygen, then they're only 90% saturated. And of course, the more saturated the hemoglobin is, the more oxygen is going to be carried. And that's why the respiratory centre increases respiratory rate. Because if you're breathing more oxygen in and out of the lungs, then you can increase the proportion of the hemoglobin going through the lungs in the pulmonary circulation, which is oxygenated. So increased respiratory effort increases the amount of oxygen going into the blood, and that will increase oxygen saturations. If the hemoglobin is more saturated, it's carrying a greater volume of oxygen. That means more oxygen is being transported to the tissues. So there's oxygen saturation. And of course, the final component is hemoglobin concentration. The more hemoglobin that is there, the more oxygen it can carry. It's like having extra trucks or putting extra trailers on the back of your truck. You increase the total oxygen carrying capacity, therefore more oxygen will be delivered to the tissues. That's the oxygen flux equation, and it explains a lot of the compensatory clinical features that we see in hypoxia. So, worth memorising: oxygen flux equals cardiac output multiplied by oxygen saturation multiplied by hemoglobin concentration.